Millions of dollars are spent every year to make online courses visually stunning and highly produced. Yet, under this chaotic overload, the system freezes. When measured, students using these flashy platforms frequently score worse on comprehension than those reading simple, static text. Instructional design fails the moment it is treated as a visual art form rather than a matter of cognitive engineering. To understand why these platforms fail, we rely on cognitive load theory. Developed by researchers like John Sweller and Richard Mayer, this empirical framework dictates exactly how human brains encode and process new information. The encoding of information is a mechanical process. It operates under strict physical limitations, completely indifferent to how modern or engaging an interface appears. To design effective educational technology, we first have to map the biological bottleneck of human memory, and then engineer specific interface laws to bypass it. When developers ignore these rigid cognitive constraints, their highly produced platforms actively prevent users from forming long-term memories. The Atkinson-Shiffrin model processes data through a three-stage pipeline. Sensory memory captures all input but deletes unfocused data instantly. Surviving data enters working memory, the hardware bottleneck, capped at 7 elements for 30 seconds. Once full, new information physically bounces off. If instructional data is not manipulated within this tiny window, it falls out of the buffer. But successfully processed data moves into the final stage, long-term memory, permanently encoded into infinite, organized structures known as schemas. The mental effort required to absorb the subject itself is called intrinsic load. But there is a second type of friction, extraneous load. This is the unnecessary processing power consumed by confusing formats, scattered, unstructured information, and poor interface design. Because working memory is rigidly finite, every ounce of extraneous load directly robs the brain of processing slots needed to understand the subject. These biological limits dictate precise rules for how information must be displayed on screen, beginning with the split attention effect. Separating a geometric triangle from its explanatory text forces eyes to continuously track back and forth. This eye travel fills working memory with spatial mapping, leaving zero room for math. The solution? Integrate text directly into the geometry, clearing the buffer for learning. This brings us to the redundancy effect, which dismantles a popular fallacy in educational technology, the idea that more information is always better. When an interface presents identical data in multiple formats simultaneously, like pairing on-screen text with verbatim audio, it forces the brain to process two redundant streams. Adding non-essential decorative graphics or fun animations to a problem acts as active interference in the processing pipeline. An instructional designer must ruthlessly strip away this extraneous noise to isolate the core signal. Every single pixel on an educational screen must be justified. It either directly aids the transfer of data into a schema, or it acts as a cognitive tax that drains finite processing power. Modern education platforms frequently push unstructured sandbox environments and discovery learning, placing a heavy emphasis on experimentation for beginners. When a beginner is asked to solve a complex problem from scratch without strict step-by-step guidance, they experience neurological gridlock. The working memory is forced to hold the problem state, the goal state, and simultaneously search for potential strategies. This is solved by the worked example effect. Empirical studies demonstrate that analyzing a fully solved step-by-step problem mathematically outperforms unguided problem-solving for beginners. Studying a solved example removes the cognitive burden of searching for the right sequence of actions. It physically prevents the working memory buffer from overflowing. This highly structured approach frees up the user's processing power to focus entirely on recognizing patterns and understanding the underlying rules of the system. For true novices, maximizing rigid structure and eliminating exploratory choice is the most biologically efficient method to construct foundational knowledge. However, there is a critical caveat to this engineering framework. The rules of cognitive load are highly sensitive to the user's prior knowledge. It is called the expertise reversal effect. The highly structured designs required to optimize learning for a novice will actively degrade the performance of an expert. On the left, a novice's working memory fills 7 slots with fragmented data. On the right, an expert retrieves a complex schema into a single slot. The other 6 remain empty. Because experts process data instantly, forced step-by-step guidance creates friction, becoming extraneous load. The operational requirement for any instructional designer is clear. You must measure and adapt to the baseline knowledge of your specific cohort before touching an interface. The educational technology industry has spent decades chasing visual trends, interactive gimmicks, and aesthetic engagement. Effective interfaces must be engineered for cognitive physics, prioritizing biological limits over aesthetic engagement or trendiness. True instructional design is about respecting the biological limits of the mind. Eliminate the noise, integrate the signal, and get out of the way so the brain can build schemas.